Hello students, in this video we'll understand the relation between x plus or the closure of x and the super key. Let's take this theorem. If we have a relation R with the following attributes or columns a1 till an, we have this as an input and a set of functional dependencies f in R, and we have k subset from R. We mean by k set of attributes. For example, if it may be a1, a2, or a4, a5, that is subset of R. So if we have R is a set of columns or attributes, and we have F, which is a set of functional dependencies, and we have that K is subset of R, then K is a super key. We say that K is a super key if we calculate K plus or the closure of K, and we find that it is equal to all attributes in R. So if we have K is a subset of R, or is a set of attributes, and we compute the closure of K plus, and we find that K plus is equal to the set of all attributes, then we can say that this K is a super key for this relation. Now if we found that K is a super key of this relation, and we need to prove that it is a candidate key, it should be a candidate key only if we go to any subset x of this K and we calculate x plus. It should be different from all the attributes in R, which are a1 till an. So we know how to determine if K is a super key of a relation R only by computing the closure of this attribute of this K, and if the result was a set of all attributes in R, then this K is a super key. Now we know that a super key may be a candidate key. If I want to prove it a candidate key, I must go for all the subsets in this K. For example, if K is two attributes, then I should calculate the closure of x plus, or the closure of each component of this super key, and when calculating, the result should be different from all the attributes in A1, all the attributes in R. Let's take an example. We have the AG plus, or the closure of AG, we calculate in the previous examples is ABCGHI, or all the set of all attributes in R, and this was the result we have got in the previous example or in the previous video, when we calculate the closure of AG, and we find that the closure of AG is equals to ABCGHI, which are all the attributes in R. Now AG, because the closure of AG is all the set of all attributes, then AG becomes a super key. Now how to prove it a candidate key? I need to go for each component of this AG, which is the first component A and the second component G, and calculate A plus and G plus, or calculate the closure of A and the closure of G. Now for AG to be a candidate key, the closure of A must be different than ABCGHI, and the closure of G must be different than ABCGHI. Now if we calculate A plus in the same way as we calculate AG, the result will give us ABCH, which is different from the ABCGHI, and if we calculate G plus, it will give us only G. Then neither A nor G is a super key, because in order for A and G to be a super key, A plus should be equal to the set of all attributes in R, and this is not the case, because A plus give us only A, B, C, H. It is missing G and I. Also for this applies for G. So because AG plus is a super key, and each component of this super key, when calculating the closure of this component, give us only a limited number of attributes, then AG becomes a candidate key. This is the way how to prove a candidate key. So in the next video we'll talk about the normal forms, which are if 1NF, 2NF, 3NF, BCNF in the next video, so stay tuned.